Uh-oh, that's not what you want to see. And neither is that. We have a lot of dead things on this board. We have at least one channel with totally dead output FETs and driver. Dead auxiliary supply for the drive ICs. This resistor here is toast. We need a full power supply rebuild of the MOSFETs, gates, and drivers. And there's also some burn resistors over here by the output terminals. Let's start with the power supply section. So we need to replace all the FETs. Remove these dead gate resistors. These toasted drivers as well. Now let's power it up and check that the TL494 here is not damaged and generating pulses. Yep, so let's put in new drivers. Need 8 new gate resistors. And of course some new FETs. Now that should be the power supply section fully repaired, but before we turn this on, we need to turn our attention to the output section and fix whatever's going on here first. Initially, I thought we had dead output FETs because we have 53 ohms between gate and source of this MOSFET. However, what I noticed is that the resistance drops even lower if we go after the gate resistor closer to the drive circuit. We actually get a dead short there. So the issue is in the drive circuit here. Look at this, a whole bunch of low resistances. We've got about 10 ohms across this capacitor. We also have the same thing going on the other side of the board. However, this MOSFET does look like it's dead because we have a dead short between drain and source, and we have a low resistance between gate and drain. So I think this FET is the one that killed the power supply and possibly spiked back, killing the drive IC on this card, and that also spiked back through the 12 volt VCC supply and killed some of the ICs on the other cards too. And the reason I think that was the 12 volt supply for the chips is because this diode here is responsible for rectifying some pulses from the transformer to generate 12 volt VCC reference to negative rail, and that appears to be shorted. So let's remove the one FET that appears to be shorted from this side, and now any low resistances to drain have disappeared. We still have a low resistance across gate and source though, and that will be a damaged drive circuit. This one next to it also appears to be dead, so let's remove that, and now let's remove those low resistances as well. So all of the other FETs in the board are okay, but the drive circuit for this one's damaged, as we saw earlier, and we know the drive circuit for this one has been damaged as well. So I'm going to go ahead and remove the IRS2092 chip from this card and this card. Sweet, that's removed our low resistance and shorts from gate to source. Let's see if the shorts across this capacitor has gone. Yes, it has. That was just the chip. What about this 12 volt VCC supply diode? No, that's definitely shorted. So let's remove that and also remove this burnt resistor from over here. Cool, the short across that diode has now gone. With where we're at now, I should be safe to power up this amplifier and check there's no voltage leakage on any of the other channels here. See if anything gets unnecessarily hot and make sure the power supply repair was good. So we have a tiny little bit of rail voltage in the board, about 3 volts. Bump it up again to about 12. So each channel has one high side FET, which is this one, and one low side FET, which is this one. The low side should have 0 volts on the back, but should have negative rail on 1 and 3. So no leakage on this channel. Low side 0. High side positive rail looks good. This one doesn't have a driver. We've got positive rail on the high side. Uh-oh, we've got positive rail on the low side as well. So that means that positive rail voltage is probably leaking from the drain of this high side FET through to the gate or source. So this FET might be damaged, or some components on the drive circuit are damaged. Ah, both these FETs check out fine, so it must be something on the driver card. Yep, that voltage leakage is still there. Hey, you know, I just had a thought. We removed this 1K resistor, didn't we, from here? I wonder whether that actually pulls down that voltage to ground and it doesn't really have any current behind it. So we have positive rail on this resistor here where it's removed. If we go to one of the good channels here, we don't actually have it on this side or on this side. So I reckon it just needs this resistor here to pull that down. Just tacked on these through-hole resistors. I've run out of surface mount ones in that size. Yep, that's better. So now we're powered up and idling. Power supply PWM looks fine. Output section's not doing anything as expected because we've removed the 12 volts VCC rectifier diode here. So you can see on this side of the diode that would lead to the drive ICs, we've got negative rail, which as far as it's concerned is ground because the drive ICs are referenced to negative rail for their ground. And on this side of the diode we have our AC input referenced to negative rail, and once that gets rectified we'll end up with about 12 volts referenced to negative rail for the drive IC supply. So we just need to fit a new, preferably slightly larger and more robust rectifier diode here. I've got some MURA115s in stock, that should do the trick. That fits nicely, so we're going to attempt to power up. Nice low voltage, keep the rails nice and low. Let's probe the output of this rectifier and see what it does. Uh-oh, we're drawing 4.5 amps and looks like we have pulsing there on that diode. Check the other side. Okay, something's drawing excessive current, preventing this from building properly and causing it to cycle. So it's possible that one of these two drive ICs also got damaged in the original failure. And wherever we've got excessive current draw, we'll also have something getting hot. So let's see what gets warm. The new diode that I've just fitted, nice and chilly. However, These output FETs over here on this channel, definitely getting toasty. Let's see what the low side drain is doing as we power it up. Uh-oh, big swing to negative rail. On this channel on the low side drain, we don't have that. It's absolutely fine. So I suspect that this driver is damaged, not in a way that presents a short when we cross the multimeter, but that causes a huge swing to negative rail on low side drain when we try and power it up, and also overloading the 12 volt VCC. So let's remove this drive IC. So now this is the only remaining channel with everything fitted. So if this one has fully survived, we should get some class D switching maybe on this channel. Let's have a look. Power up. Let's make sure the 12 volts builds fully. Yep, there we go. Let's check the low side drain of this channel. Uh-oh, a big swing to negative rail. No excessive current draw though, but yeah, something's not right on that channel either. So I imagine that in the original failure mode, all of these 4 drive ICs got damaged just in different ways. And so yeah, that one's probably toast as well. Okay, 4 new 2092s. These are not cheap. So I've just fitted one replacement 2092 to this driver card just to see whether that is the only issue left now with this amp with these 4 drive ICs. So if we power it up, 9.6 volts, low side drain, we do get class D switching. So provided there's no other issues with these other driver cards, I'll just fit these new chips, replace these resistors over here, and it should be good to go. So with all the drive ICs and new FETs fitted, let's power it up and check we have class D switching on all 4 channels. So again, keeping the rail voltage nice and low until it's back in the heatsink. Channel 1. Class D switching, channel 2, Class D switching, channel 3, Class D switching, lastly channel 4, oh yes!